My senior design project was to take in CT scans and turn them into a 3D volume. I accomplished this using the Marching Cubes algorithm. For a set of images, I iterate over the images and calculate the alpha value of each pixel. The alpha value of each pixel represents the density of the tissue at that point. I calculate the alpha value by summing R plus G plus B divided by 3, and using this alpha value to represent the density of the tissue at that point. You can see on screen 20 layers of a rabbit chest CT scan. I am showing here the various densities that can be shown. I can either show all tissue densities, the first that you just saw, medium densities, which would be muscle, lung, other organ tissue, and low density, which would be stuff like fat and air. To select the image directory that you would like to turn into a 3D volume, you click the Select Image Directory button and select the directory you'd like to open. After opening it, you can set the number of threads that you would like if you want multi-threaded application. You then can click the Create 3D Volume button. The loading progress bar shows the progress of the app as your 3D volume is being built. There are also the options to enable color mapping, to show a scroller plane, which, as you scroll it up the rabbit, will show the corresponding CT scan that created that layer. So these are the 2D images that correspond to this point, that plane in 3D space. There's also the option to enable opacity, and this can kind of give you a little bit of a glimpse into what the inside of the rabbit looks like. One of the biggest challenges I had in my project was thinking about speed and optimization. Unfortunately, when I first ran this, to get all 801 layers rendered took up to 45 minutes, which was prohibitively slow. What I was doing before was when I took in each of the images, I created what was called a world, which was basically a map of tuples. So the 3D address of each pixel from each image in 3D space, stored in a map. Then, when I wanted to actually create the structure, I would iterate over all these positions in the map, and I would use the imaginary grid to determine how the triangle should be drawn by using the Marching Cubes algorithm. This grid, each grid has 6 corners. Each grid cell has 6 corners, and each of these 6 corners have a certain density assigned to them by the voxels surrounding them at this point. These densities would determine how many triangles should be drawn, thus giving the resulting images. However, by using this 3D map, I was having an O of n cubed time as I was iterating over first all x's, then all y's, then all z's. I originally tried to fix this problem by multi-threading my application, which did have a big improvement. It went down to 20 minutes, but that still wasn't fast enough for me. On Adam's advice, I decided to convert my data structure from a map to a 1D array. So now 1D indices represent a 3D address, and I have a method of converting back and forth between the 3D address and the 1D address. Now, to load 801 rabbit layers takes 4.5 minutes. In the future, I would still like to be able to get this faster, but I'm very pleased with the progress from 45 minutes to 4.5 minutes that I made. So you can see on screen the different density selections being shown. And now here's another CT scan that I also volumized. This is of a heart and the chest cavity. You can see from the different renders the rib cage here and some of the spinal cord, as well as some other high density veins that have gotten included as well. You can see with the color mapping that everything's mostly yellow and red. This is the medium density. Again, you see different areas. Now you see more of the veins showing and less of the bones, although you still see some of those. And on the next one, you'll see fat. In the future, it would be nice if I could get my density selector to be smarter, but I'm very pleased with the different thresholds set for now. Thank you so much. I really had a great time making this.